The next example of Gibbs sampler is example with pumps. This example is also supplied in the Winbox exercise examples. So you can find it in the as solved one in Winbox. But let's take a look what is below the hood. The pumps data was analyzed and in a similar fashion in the paper by Ed George, Udi Makov, and Adrian Smith in 1993. So data come from that paper. And the data are the following. There are 10 pumps that are working correctly or failing. And the number of failures during interval of time is monitored. So for example, pump 1 is working 94.32 time units, and during that time failed 5 times, and so on and so forth for other pumps. So we are interested in estimating the rate of failing if the failures are modeled as Poisson distribution. So xi, the number of failures, are Poisson. The parameter theta is the rate of failing, but of course the number of failures depend upon time, so the Poisson parameter is theta I times Ti. The longer the pump works, the higher the rate of failing is. That Poisson distribution is proportional to theta I raised to the xi, e to the minus theta I Ti. The constants here are ignored, only the parts that contain theta I. Now, next stage is to put the prior on theta I. And we put the gamma prior on theta I. Here we assume the hyperparameter alpha is equal to 1, and that fixed one, so that prior on theta I is simply given by this expression. It is exponential distribution with rate parameter beta. And finally, beta is also given prior. And beta is given gamma prior with hyperparameters C and D. So the prior on beta is given by this expression. Hyperparameters are C and D. We are interested in theta. So we multiply pretty much everything here to get joint distribution. What we multiply here is the likelihood part times the prior for each pump separately. So we get product from I equal 1 to n of the likelihood times prior, and then times the hyperprior here. So we got from here beta. This part is also part of the likelihood times prior, and then we got the hyperprior. Now we need to derive from this joint distribution full conditionals. So we fix theta I and we condition with respect to all values which are not theta I. So thetas for I different, for parameters different than I, indices different than I, beta and data. And when you select only a part that contains theta I, you end up with gamma distribution with parameters xi plus 1 and beta plus ti. And finally, you need a full conditional for beta, and that one is also gamma distributed. The parameters are m plus c and summation of theta i's plus d. So now we have the full conditionals, and then we have starting values for thetas and beta, and then we simulate from these gamma distributions to get ultimately sample from the posterior. Again, beta is not of our interest. This is the hyperparameter of the prior, but thetas are of our interest. So let's take a look at pumps mc.m.